All right, so this is, I guess, our flipped classroom lesson on primary trig ratios word problems. So it's Tuesday evening right now. So today we looked at primary trig ratios in class, sine, cosine, and tangent, and we looked at how to use each one of them, how to plug them into the calculator, and the homework that I assigned to today was to basically get practice at solving for missing angles and missing sides. Just the triangles on their own, no word problems attached, just an image of a triangle. So you should have worked on that tonight. That way you could be ready to watch this video either tonight or probably sometime tomorrow is probably when you're going to watch it. My suggestion would hopefully be during tomorrow's foundations period or tomorrow evening. And I'm going to give you homework at the end of this as well. The goal here is that you've watched this video and you've taken notes and you've followed along. Even if you're not getting it 100%, that's fine. Just follow along, make notes. I will give you a hard copy of this note on Thursday, and you can transfer what you've written today onto that if you want. But the goal here is that you've gone through this video and this note so that on Thursday, rather than me having to teach all this stuff fresh, you already come into class having an understanding of this stuff. I can take up some of the homework questions that I'll assign to you tonight and anything else that was unclear in this video, but then we've got another day for you to work on problems in class. So you have more time to do seat work rather than me up at the board in front of the class. And then I can also move on a little bit more if I can as well, so that way we can pick up the pace a bit and we have a bit more time for exam review at the end. Okay, so let's start with this. So before we actually get into looking at the word problems, there's a couple of terms that I want to show you. And so this is on my computer, so I'm going to kind of zoom in a little bit. So you see a couple terms here. You've got angle of elevation. Where's my mouse so I can do this? So angle of elevation and angle of depression. So what that basically means is if you are, imagine this is eye level. So here's your person and this is an eye, right? So this is at eye level. So if you're looking straight ahead, you've got this horizontal sight line, right? So the horizontal sight line is basically what you see if you look straight ahead, right? So not using your peripherals or your outside vision, just looking dead center in front of you. So from that, imagine if you were standing up and you were to hold your arms out. So I know you can't see my arms, but imagine you're holding your hand out like this, right? And so you're holding your arm out at eye level, right? So anything that's above you would be an angle of elevation. So you could tilt your eyes up and look up, or holding your hand out, you could look downwards towards your feet. So up to the sky or down towards your feet. And that forms an angle. So from the horizontal sight line, comparing from that line, if you were to look up, that would be an angle of elevation. So for example, if you were to look 40 degrees upwards, you would be looking 40 degrees up from the horizontal sight line. So this angle right in here, let me get the pen. So this angle in here would be, say, 40 degrees, right? So if I said to you, oh, look up 40 degrees and, maybe you'll see the sun up here. Or looking straight ahead, I might say, okay, now look down at your feet. And so you will have to look down. And let's say you have to look down 40 degrees. So this angle would be your 40-degree angle down, so an angle of depression, okay? So that's important because a lot of times when you get some of these word problems, they'll mention angle of elevation, angle of depression, and you just have to understand what it looks like and how to draw it. So angle of elevation is looking up from straight, and angle of depression is looking down from straight. So let's try the first problem. It says, a searchlight is mounted at the front of a search and rescue helicopter. The pilot is flying the helicopter at 150 meters above the ground, and the beam hits the ground at 70 degrees from the horizontal, so the horizontal sight line, in other words. The beam spreads out at an angle of 5 degrees from the searchlight. How wide is the beam when it hits the ground? So I'm going to switch over here now, and I've just got regular paper here, and I'm going to kind of work through it. I might have to cut the video at times so that I can refocus and stuff. So if you don't see anything, don't worry about that. So with these problems, the best strategy is to draw out a diagram, because I might give you a diagram, I might not. So you kind of have to be able to draw a diagram from what you see, or from what wording is given to you. So a searchlight is mounted at the front of a search and rescue helicopter. All right, so let's just start with that. So you don't have to draw a helicopter if you don't want. I'm going to make an H. Hold on. I'm going to How can you see this? I can't really see through the phone. I have to look at the paper at the same time. How did I do this last year? All right, so I'm starting off with H. So H is going to be a specific point on the triangle. And so that's my helicopter. So my search and rescue helicopter is here, and my light, is somewhere here. It doesn't really matter. It's a point. The pilot is flying. Let me go back to the thing so you can see it here. The pilot is flying the helicopter 150 meters above the ground. So if I was now to go back here, I've got my helicopter, and the pilot is doing that 150 meters above the ground. So here's my ground, and I know that the height is 150 meters. So the helicopter is 150 meters from the ground. And the beam hits the ground at 70 degrees from the horizontal. So my horizontal would be directly ahead of the helicopter. So, this is just a sketch, but I'm kind of drawing a dotted angle. And the idea here is that this would be a 90-degree angle, right? Because if you've got a helicopter that's directly above the ground, and then you're looking at the horizontal, which is straight ahead, that would be 90 degrees. Okay, so if they're saying that the beam hits the ground at 70 degrees from the horizontal, we're talking about a angle of depression. So a 70-degree angle of depression. So the light shines down. So here's my light, and it shines down at an angle of 70 degrees from the horizontal. So it doesn't mean that this is 70 degrees with the ground here. It means that this is 70 degrees, right? 70 degrees from the horizontal. Right? And then it says the beam spreads out at an angle of 5 degrees from the searchlight. How wide is the beam when it hits the ground? All right. Sorry, so I just took a break for a second there. So the last part of the question says, how wide is the beam when it hits the ground? The beam spreads out at an angle of 5 degrees from the searchlight. So basically what they're saying is, if this was the searchlight, we would have sort of another triangle that's sort of forming here. So this whole thing here would be the beam of light, right? And it gets wide. Think about like if you were to take a flashlight and you were to hang it on an angle and shine it at the ground, you would see like the light spread out, right? Because it gets wider. So this little bit here would be 5 degrees because it spreads out at 5 degrees. And this would be where the light strikes the ground. So this whole width here would be the beam. So I've got the ground to the light, and then, or the beginning of the light and then the end of the light. And you know that the ground is going to make a 90-degree angle here too. So I've got two triangles here. I've got this one. Sorry, I know it's blurry. It's because I'm switching back and forth between the screen and this. And I've got that triangle. So I've got two triangles. What I'm trying to find is how wide the beam is when it hits the ground. So in other words, L to B. So I'm going to mark that off as X, that length. That's what I want to find. Sorry, guys. Come on. No? Okay, there you go. Maybe I'm going too close. All right, so I'm trying to find X there, so that little LB piece. So if I'm going to find that, the first thing that I need to do is I need to find, you have to work backwards a lot of times. So if you think about it, this little triangle here is not a right triangle, so you can't use any primary trig ratios. But you've got this smaller right triangle and then the bigger right triangle with X. So you kind of have to be logical here, okay? So the first thing that you're going to want to find is the length of this whole piece at the bottom. So G all the way to B. So we could say that G all the way to B is Y. And if I find that entire side, then I can find just my smaller portion there. So let's start with finding side Y. So remember that we have to use primary trig ratios. So I'm going to write here SOHCAHTOA, in case you don't remember. And it helps you to figure out which one you're going to work with. So remember that this is a 90-degree angle. So if this whole thing is 70 degrees, remember this 5 is a part of that 70. So it's almost like this is 65, this is 5 because the angles, it's spread out there. And to be fair, I maybe could have done it 5 on the inside there. It wouldn't really, you'll get a different answer, That just sort of comes down to the interpretation of the question. So I'll accept it either way. Because it's saying that the beam hits the ground 70 degrees from the horizontal. So I could have drawn this 5 degree wide beam. I could have done it on the inside. So this side rather than this side. Okay, it'll give you a different answer. I'll leave it up to your interpretation. This is how I interpreted the question. So if this is 70 degrees, this in here has to be 20. Right? So I'm trying to find this side. So I'm working with this smaller triangle here, right? So GHL. And think about what we did today in class. So you look at your angle of interest, which is 20. And I think about, well, what do I have in relation to that angle? I have y, which is directly across from 20. So it would be my opposite. And I have the side that is right beside my 20. So that would be my adjacent. So if I have opposite and adjacent, I'm working with tangent, right? Tan is opposite and adjacent. So tan of an angle is equal to opposite over adjacent, right? And I can start plugging in. So I can say tan of 20 degrees is equal to y, which is my opposite, over adjacent, which is 150. And then I can solve. I've got my calculator here. I don't know if you're going to be able to see what I'm typing in. You know, forget, I'll just calculate it on my own, and you should be doing the same anyway. So I've got tan of 20, not tan inverse, right? Because I'm trying to find the ratio. So tan 20 gives me a number multiplied by 150 because I'm cross multiplying, and I get y is equal to, let's do 2 digits. So I got 54.595. So if I round that, I'm going to get 54.60 meters. So that's my y distance, okay? But I want x. So I have all this y. There's no way I can find the x directly. But if I find GL, which I'm going to call W, if I find, it doesn't matter, it's any letter. So if I find G and L, then I can get my entire side. Hold up. Okay, sorry, I made a mistake. And this is what sucks about videos, because I can't go back and edit now. So bear with me. If we're talking about 20 degrees here, then this is the side that we found. So we didn't find y, we already, that was w. I apologize. You don't have to do any changes to the calculations, it's just that's w. Right? Because I plugged in 20. So if I'm looking at angle 20 degrees, I'm only referring to everything up until this point. So I'm just looking at w. Okay, so that calculation gave me w. Let me fix that too. Sorry. I would have rehearsed these beforehand, but then all the drawings would be done. And then I want you to be able to see the drawing, so. All right, so now I want to get y. So now I'm going to get this entire piece, so from G all the way to B. That means I need to look at this whole triangle. So remember that I've got, oops, sorry. Come on. I've got 20 degrees plus the additional 5, right? Because it's 5 degrees wide, the beam there. So I've got 20 and 5. So 25 degrees is what I'm working with this time. Other than that, it's the same ratio, right? Because I'm still working with the same sides. I'm still working with an opposite and adjacent. The only difference is my angle is going to be different. Now it's 25. So tan of 25 is equal to y over 150. So I'm going to type that in my calculator. Tan 25 times 150 equals, so y equals 69.95 meters. Okay, so I've got y and I've got x, or I've got w, sorry. So now to get x, it would be pretty logical. I just need to subtract them, right? So I know that x is going to be equal to y minus w. So x is equal to 69.95 minus, sorry, I'm trying to do this through the camera, 54.60. And I get x being equal to 15.35 meters. Okay, so that's x. So that answers my question. How wide was the beam? Okay, so this is nice because I don't have to say any questions because you're not here. So let's move on to number 2. A student is standing at the top of a hill that is 200 meters high. Using a clinometer, which is basically just a device that you can measure angles, like large angles or large scale angles. She sights the base of the hill at an angle of depression of 40 degrees from the horizontal. If the slope of the hill is constant, how far will the walk from the top be to the hill of the base? All right, that's probably an easier question, actually. So I'm going to get my SOHCAHTOA going again. Oops. This is very difficult to hold a phone and do this at the same time. All right, so let's start by drawing a diagram. So also this is gonna be on Schoology, this video too, so this note, so you can always go to Schoology and get the note. A student is standing at the top of a hill that is 200 meters high. Okay, so we'll start with that. So here's our student, and she's at the top of a hill that is 200 meters high. So you can imagine that there's, a little hill or a little mountain there. That's not important, right? I'm just kind of giving you a visual there. All we care about is how high that actually is, what's actually going to form the triangle. And we know that this is 200 meters high. Okay? And this is the base of the hill, so we'll put G, ground. Using a clinometer, she sights the base of the hill at an angle of depression of 40 degrees from the horizontal. So what that means is, if she's standing here, here's her horizontal, right? It's the eyesight line. So if she's from the horizontal, she says she sights the base of the hill, so she can look down at the base of the hill, the bottom of the hill, at an angle that is 40 degrees from the horizontal. So that means if I was to draw a line all the way down to the base of the hill, right? Because this is the part of the triangle that I actually care about. This here is 40 degrees, right? The angle from the horizontal, the angle of depression is 40 degrees. If the slope of the hill is constant, so obviously we know that the slope of the hill, it's going to be a little bit bumpy, but assuming that the slope of the hill is constant, like the triangle that I drew, how far will the walk be from the top to the hill of the base? So here's the rest of my hill, just to complete off my triangle. I don't know what you want to call this. Let's put B for like base of the hill. Okay, so what are they asking me to find? Oh, first of all, you know that you can assume that's a right angle. So they're saying how far is the walk from the top of the hill to the base. So in other words, find this. Find the length of that side. So I'm going to mark that off as X. I'm trying to find that side. So I got to go, right, well, what angles do I have? Well, I don't have an angle in the triangle, but I have an angle outside of the triangle. I know that the angle of depression is 40 degrees, which means that this here has to be 50 degrees. Right, because I know that's going to make a 90-degree angle, right? The hill and the horizontal makes a 90-degree angle. So if the angle of depression is 40, the angle inside is 50. So what I'm trying to find is side X. So I go, all right, well, what do I have, right? Well, I have 50 degrees. That's my angle of interest. And now what do I have with respect to that? Well, I'm trying to find X. X is directly across from my right angle, right? So I know I'm looking for this side. The side opposite the right angle is called the hypotenuse. So I have the hypotenuse. What other side am I given? It is beside my angle of interest. It's adjacent to it. So I have hypotenuse and adjacent. Which trig ratio involves hypotenuse and adjacent? Cosine. Adjacent hypotenuse. So we know that the cosine of theta, or any angle, is equal to adjacent over hypotenuse. Sorry, if I'm pausing, it's because I'm trying to get this to focus. So my angle of interest, or the angle that I know, is the 50 degrees. So that's what I'm plugging in for theta. So cos of 50 is equal to my adjacent side, which I know is 200, divided by x, which is my hypotenuse. That's what I'm trying to find. So the same thing we did in class, we cross multiply, so we get cosine of 50x equals 200, and then I can, in order to get x by itself, I'm going to divide by what's attached to x. So I'm going to divide by cos 50, divide by cos 50, those cancel out, and I'm left with x equals, and then I go to my calculator. So I've got 200 divided by the cosine of 50, and I get 311.14 meters. That's it, done. Okay, key here is drawing the diagram, drawing a logical and correct diagram, and understanding what degrees are what. So what measures are referring to what, right? Unfortunately, that's not a teachable skill. So that's not something that I can teach you the same way that I can teach you how to use these ratios. That's something that you're just going to have to develop on your own as you practice. And that's why homework is so important, because the more of these you do, the more apparent it'll become. It'll be obvious to you, right? Like when I look at these questions, right away I know what angle is what, right? And it's not because I'm a math expert. I'm not, right? So I look at this and it's, from practice, it stands out to me what's what. So you have to do that practice so that you know exactly what it is that you're looking at and looking for. All right. Let's move on to the next one. Two more, right? There's 4 examples altogether. So from the bridge of a boat on the Niagara River, the angle of elevation to the top of Horseshoe Falls is 64 degrees. The angle of depression to the bottom of the falls is 6 degrees. If the bridge of the boat is 2.8 meters above the water, calculate the height of the Horseshoe Falls to the nearest tenth of a meter. All right, that's a nice one. So we start off with the bridge of a boat. I don't know if you guys know what the bridge of a boat is. The bridge is like, how do I explain it? Where's Owen when you need him? If you have a boat, right, and, whatever, there's my boat. So the bridge, I believe, is like the front part. So, I'm not talking like a sailboat. I'm talking like a ship, like picture the Titanic or something. So, you've got all the windows, right? All the different areas or whatever. And then you have the front part of the boat where the steering wheel is, the captain hangs out. Everything is sort of run. It's like the control center. So it's, pretty high up off the water. If you think that this is 5, 6, 7 stories tall, it's pretty high up. Okay, so that's why they're telling you that it's 2.8 meters above the water. So, you know what? Let me get a fresh page going. Okay, so let's start with the bridge of a boat. So here's my boat. And my boat is 2.8 meters above the ground. So I'm actually going to just draw a little boat. And the B is representing the bridge, so where I'm starting from. So from the bridge, it says the angle of elevation to the top of Horseshoe Falls is 64 degrees. So Horseshoe Falls would be a waterfall, in case you don't know. So here's your waterfall. Here's your waterfall. Yeah, originally they actually asked me to be an art teacher. But I said no because I thought I was too good at art, as you can see. So there's my waterfall. So the top of Horseshoe Falls, right here, is at an angle of elevation of 64 degrees from the bridge. So if I'm talking about an angle of elevation or depression, I need to have a horizontal, right? So from the bridge, I have a horizontal, that's straight ahead. So my angle of elevation is the angle above that dotted line, above that horizontal. So this is 64 degrees. The angle of depression to the bottom of the falls, let me just switch back so you can see it. The angle of depression, that should say to the bottom, not of the bottom of the falls, is 6 degrees. So again, from that horizontal, going back down to the bottom of the falls, the angle of depression is 6 degrees. If the bridge of the boat is 2.8 meters above the water, calculate the height of the horseshoe falls to the nearest tenth of a meter. So what you have here is two triangles, and I'm going to try and make that a little bit straighter so that you can see it. Okay, so you've got two triangles. You have this one and this one, two right triangles. I guess I should be more specific. You know that the horizontal makes a 90-degree angle with things that it goes through, right? So here's your boat, here's your horizontal, it runs straight through, and it's going to intersect your waterfall at a perpendicular angle at 90 degrees. So you know that this is a right triangle, a right angle here, and this is a right angle here. Because the bridge of the boat is 2.8 meters above the water, right? Here's your water. Here's water level. I guess it's not accurate because, I don't know, let's just, whatever. There's a water level. I know it's slanted. It doesn't matter. You know that the boat is sitting in the water, and you know that the bottom of the falls is in the water. I just drew my falls too long. So you know that the height of the boat is 2.8 meters, or the height of the bridge of the boat is 2.8 meters. Well, if the height of the bridge of the boat is 2.8 meters above the water, they tell you that in the question, right? If the bridge of the boat is 2.8 meters above the water, so if the bridge of the boat is 2.8 meters above the water, that means that this length here, from this horizontal down to the bottom of the falls, is 2.8. That little piece there. So from the horizontal to the bottom is 2.8. So what I really want is from the horizontal up to the top. So I'll mark that off as side X. That's what I'm looking for, right? So what's kind of nice is a lot of this stuff is useless to me, right? I don't care about what's happening down here because I've already got the height of that triangle there. So what I need is this, right? So, well, what do I have? Oh, actually, I do care about that. Oh, I'm so crafty. All right, I definitely need that. Okay, here's why. Because if I'm trying to find this side, I go, okay, well, I need to find this side. What's my angle of interest? Well, 64. All right, fine. But I need to have at least one known side in order to do this, right? I've got this, but I don't know this, and I don't know this. So I can't use a ratio to find this. I need one of these sides in order to go any further, right? Well, logically, I'm not going to get this. There's no way I'm going to find the length of that side. But because this triangle and this triangle share that horizontal, that dotted line, I can find the length of the horizontal by using the other triangle, the small one. If I find the length of the horizontal, now I have a side and an angle. Now I can find my other side. So I do need to work with this down here. So I want to find the length of my horizontal. So in other words, in terms of the question, how far is the bridge of my boat from the waterfall, right? The distance from the bridge to the waterfall. So I'm looking for this. I'm going to mark off my horizontal as y, and I'm going to solve for y first. So I go, okay, well, what's my angle of interest? In this case, if I'm looking at my small triangle, my angle of interest is 6 degrees. Okay, what do I have? I have the side opposite to that. I'm trying to find the side adjacent to that. So opposite and adjacent is tangent. So I'm going to say tan of theta. Come on. Is equal to opposite over adjacent. Okay, and then I can plug in. So tan of 6 degrees is equal to the opposite, which is 2.8, over my adjacent, which is y. Solve. Cross multiply. Tan 6 y equals 2.8. Divide both sides by tan 6. Tan 6. Cross those out. Y, sorry, I didn't mean to clear my throat in your ears. y is 2.8 divided by tan 6. 26.64 meters. So that's y. So that gives me the distance from the bridge to the waterfall. Now that I know y, now I have a side and an angle, so now I can find my other side. Okay, so now let's go back here now. Trying to find this side. So now I'm working with this bigger triangle. What is my angle of interest? That one. What do I have with respect to 64? I have the adjacent, because I just solved for it, 26.84. I'm trying to find my opposite. So once again, opposite and adjacent would be tan. So I'm just going to solve that one now. So tan of 64 is equal to opposite, which is x, what I'm trying to find, over adjacent, which is 26.64. Yes, cross multiply. So the tan of 64 multiplied by 26.64 gives me x is equal to 54.62 meters. So that's my x value. So that's this. They want to know, calculate the height of the Horseshoe Falls to the nearest tenth of a meter. So I already know what x is, or I know what x is now. I know that I had an additional 2.8 meters. So obviously just to this number add 2.8. And you're going to get 57.42 meters. And that's the height of Horseshoe Falls. Yes? Yes. Good. Last question. Now, all these questions are just finding the side lengths. The angle ones are pretty much the same. You're just using the inverse, but you're doing the same thing. You just would be given two sides and being asked to find an angle rather than doing an angle and a side and asking you to find the other side. However, you can always, I can always do some of those with you if you would like in class on Thursday, because I will assign some of those as homework. So if you want to do that, you can ask me about those on Thursday. All right, let's look at the last one. Okay, I'm hoping you can still see normal color because it's 9 o'clock, so my blue light filter just went on. So now the screen's kind of reddish, which is fun, but I'm hoping that that's what it looks to me. I don't know if when it's videotaping what it'll show, so hopefully you're not seeing red. And if you are, sorry, but not sorry.